very much. It's nice to be here for the first time in Perimeter, and my subject today is double field theory. I think this volume is a little too strong. So this is work done in collaboration with Chris Hull. And a paper on this subject appeared about a few weeks ago, maybe 3 or 4 weeks ago. So the scheme of my talk is going to be a brief introduction. I'm going to talk about double diffeomorphisms. A free theory. This is double field theory, so it will be a free double field theory. About interactions, T-duality, and some open questions. Of which there are, in fact, many open questions. So let's get started quickly. So what is double field theory? Basically, it's an attempt to formulate within field theory something, an effective field theory, perhaps of massless fields, that includes some of the magic of T-duality. Now, this is a rather interesting subject, has some history, mostly of failed attempts, and not very systematic ones. So, in fact, it was not very clear at any stage what would be the problem in constructing such a double field theory. So, why double? Basically, you know very well that if a string lives in a compact space, it can wrap, and therefore has, in addition to momentum modes that represent perhaps little strings going around the circle, you have big strings wrapped a number of times. So strings have momenta and winding when you have a torus. And therefore, from the viewpoint of additively conserved quantum numbers, there's a momentum quantum number, a winding quantum number, and there are dual coordinates associated to them. The x's of the tori and some new exotic coordinates that are conjugate to winding. Now, in a sense, the field theory that lives on a torus lives in the double space. Now, this is not, I want to emphasize, and I will make it clear probably as the talk goes around, this double space is not an auxiliary space, it's not a gauge space, it's not a formalism, it's real. It is the conventional way in which you should really try to do the field theory of T-duality. So this will become clear. And nevertheless, field theories in double spaces, in fact, have not been formulated. What I will show you today is the beginning of a formulation of that field theory. Even when you simplify it a lot, it has very interesting properties. And if we succeed one day in completing this construction, it will definitely be very new. And you will see why. So let me review the setup. The setup is closed bosonic strings on a torus. So closed strings on a torus TD. So you have a two-dimensional action. It's familiar, the first quantized action. For strings moving on a torus, it will have, with a worldsheet metric, here are the string coordinates. here is a space-time metric. Here is the second term with an antisymmetric tensor. Now, these coordinates, the string embedding coordinates with this index I could split them into coordinates that I could call xa and x mu. Mu would be the uncompactified coordinates, the normal coordinates, the ones that stretch and are never compactified. And these are the compact ones. It is convenient in this notation, when you have compact coordinates, to normalize them so that the radius of the coordinate is conventionally set to 2 pi. This is the coordinate radius, but lengths, the length of the tori, are of course specified by this metric. Now, these are the so-called background fields in a toroidal compactification. They're both supposed to be constant. They're constant background metric and antisymmetric field, and they are, in general, grouped together into an EIJ, which is GIJ plus BIJ. And if you want to know in simple cases where you have tori of some radii and no background field, for example, you would set GAB equal to RA squared delta AB. And you really want to be precise, you can put an alpha prime because of units so that GAB has no dimensions in here, no length dimensions. So we are going to avoid this split. I'm going to think as if everything is compactified, but don't worry about that. I'm really not compactifying time, which would be a very delicate thing to do. And the whole thing that I'm going to tell you can be done with some indices in which I carefully distinguish compactified and uncompactified. So, but that's not worth it. So I will just write xi's from now on and think as if all of them were compact. So everybody's curled up. So if you think of these coordinates, xi of tau and sigma has an xi plus a wi sigma for the winding plus tau, g, ij, pj, and things like that in the mode expansion. These are the windings. Sigma goes from 0 to 2 pi. Those are integers, in fact, so that corresponds to the compactification of the coordinates over here. You also have 2 pi, the canonical momenta of tau and sigma that begins with pi plus other terms. You have dual coordinates, xi tilde of tau and sigma, little xi plus pi sigma plus tau, some terms, and other things like that. These are the so-called mode expansions. And if you think about it, in first quantization, you really sort of begin with these two, the x's, the ones that you have in the action, and the p is the canonical momenta. But you can invent the dual coordinate that is also an interesting object in the theory. Now, the fact is that there are winding states in the theory. There are these states. These are the windings, and there are the momentum operators that correspond to momentum states. So there is a doubling of these zero modes, and this is represented in commutation relations. So we have that the normal xi with the pj have a commutation relation delta ij, and that's also equal to the commutation relation between the tilde j's and the wi's. The x tilde are the conjugate to the w's. That means, in particular, that you can think of the pi as derivatives with respect to xi, and of the wi as derivatives with respect to the I tildes. Any questions? Yes?
Analysis for any general orbit for CFT that has twisted sectors.
That has what?
Twisted sector.
Well, probably nothing much prevents you. As long as you have closed strings and you have winding states, you can do so. So I'm just considering the simplest possible example, just plain toroidal compactification.
Okay, how is the dual coordinate defined?
How is what?
How is this dual tilde defined geometrically this way?
Geometrically, basically, when you do the quantization of this theory, you discover that the x's can be written as some x's that depend on tau minus sigma and some x's that depend on tau plus sigma. And basically, the x is really the ones in which you add them, and the x tilde is the one in which you subtract them.
When you do the integration of over the worldsheet embedding, you only integrate over x, not x tilde.
That's right. I only integrate over x. So that's why in first quantization, people have said, well, the dual coordinate is something that can be useful, and it's sort of its status has been a little unclear. So, but let me continue and see what's going to happen. Let me mention one more thing, that the PIs have eigenvalues Ni that are in the integers, and the Wi's have eigenvalues, say, Mi, that are also in the integers. And we saw here the eigenvalues here, and the Pi, well, we know how they must be quantized, but it's also consistent here with the identification of the dual coordinate. Now let's look at string states. Yes?
So do you think there's a regime where you can decouple all the oscillator modes?
Sorry?
So it seems there doesn't seem to be a regime where you can decouple the oscillator modes, right? I mean, just like, let's say the mass-wise. So basically, there does not seem to be a regime where the oscillator are both lighter than the winding and the momentum.
That's right.
So in what sense you want to decouple them?
Yes, we'll talk about this more. Indeed, certainly, if you think of excitations, getting to the physics of these excitations, we know that for small radii, winding modes are very light, but momentum modes are very heavy. And for large radii, it's the opposite. Winding modes are very heavy, and momentum modes are very light. And there's no regime in which both momentum modes and winding modes are very light. So you might ask, how can you do an effective field theory of that? And that's an important question. We are not going to attempt to obtain this field theory by taking some sort of alpha prime expansion or something like that. We're going to go in a different route. But it's a very natural question. It's the key why this theory is very non-trivial, because it's not just a simple low energy limit of the string theory. So let me talk about the states so that it becomes clearer what we have in mind. So what is a typical string state? Well, you must sum over winding and momenta. And you have objects with some polarizations, say like that, I1 up to IP, J1 up to JP, that depend on the winding and momenta. You have oscillators, alpha minus 1 I1 up to alpha minus 1 IP, alpha bar minus 1 J1 up to alpha bar minus 1 Jp. And you're acting on the momentum unwinding eigenstates. So that's a typical string state. Those are the string states that you are familiar with. I'm ignoring ghosts. They will play a minor role here. And basically, there's vertex operators for states that have momentum unwinding. Those exist. So these are the coefficient functions, the polarizations, and in a sense, those are the fields of the theory. In fact, since you have fields that depend on these quantities, it's natural, it's the obvious thing that you can define the coordinate space versions, Jp, of x tilde and x, which are the usual things, mi, nj, psi I1, psi J1, of m and n, e to the I, mi x I tilde times e to the I n I x I. So Fourier transform. You see, you have states with momentum unwinding units. Well, take the polarizations, Fourier transform them. For each additively conserved quantum number, you have a coordinate, and you are naturally led to fields that have this. So as long as you believe the string theory has vertex operators with momenta unwinding, you are just accepting the fact that fields are doubled. And this is not a trivial gauge dependence. This is not an auxiliary coordinate. This is very physical, corresponds to states that have winding. So here is the catch. Basically, here's the statement. Double field theory is what closed string theory is. We should try to formulate this. So there's one more thing to this that is important. The states must satisfy, string states satisfy the condition L0 minus L0 bar on the states must be 0. This is very different from the condition in which you have a plus. If you have a plus, it is the on-shell condition. L0 plus L0 bar should kill the state. If you have a minus, it is the subsidiary condition that must be satisfied by any closed string state. It's not a condition you can consider as a field equation. It's a condition that must be implemented from the very start. This is because this operator, of course, generates translations, sigma translations of a string, and represents the fact that the origin of the closed string is undetermined, and it cannot be fixed by any procedure known to anybody. Therefore, this condition must be implemented from the very start. What does that condition give? If you remember a little of your toroidal string theory, it actually says that the difference between the left and right number operators must equal to the product of momenta times winding on every state. So we can consider, for simplicity, fields that would correspond to what we call massless states in string theory. So what are they? Well, there are the alpha minus 1 I, alpha minus 1 bar J. You want to be precise, you actually should put the ghosts, P and W. Here is a field, E, I, J of P and W. This is a massless field. It has n equal n bar. In fact, both, in some sense, you can call them 1 or 0. More appropriately, 0, both the normal oscillators, the barred oscillators, the indices are up to 0. This is a very important massless state. It's probably familiar to you, although I will remind you in a second what it is. There's a D of P and W also that comes with C1, C minus 1 minus C1 bar, C minus 1 bar. And it's what is called the dilaton. Also has n equal n bar equals 0. And therefore, these two states of string theory, these important two states, must satisfy in string theory this condition, which says that the product of their momenta under winding must be 0. Now, we've seen what this is, Pi, Wi. Those are these derivatives. So in terms of fields that I would call Eij of x and x tilde, just Fourier transforming, and D of x and x tilde, both of these should be annihilated something I can call delta, which is essentially di tilde. It's like a funny Laplacian. It's one condition. Di tilde is what Pi, Wi equals 0. I can put some numbers to make it look better or more precise. Minus 2 over alpha prime di. So this operator must kill this field. So this is an important subsidiary condition. Presumably, one cannot do string theory unless one puts this condition. So in terms of the double field theory, these fields come with this constraint. Naturally, what are these EIJs? These EIJs are nothing else than the fluctuations of this background EIJ. So let me just write it here. You could think of a EIJ total field, which is EIJ plus a vertex operator for a fluctuation, which would be EIJ. And that would be equal to GIJ plus Bij, and you could split this Eij into Hij plus Bij, and this can be thought as the fluctuation of the metric, and this can be thought as the fluctuation of this guy. So it should be perhaps clear, and you should keep in mind that this Eij is nothing else that is not a symmetric field. It includes both the fluctuation of the metric and antisymmetric tensor field. And it also, as it is born in string theory, the second index has a different nature from the first. The first index is associated to oscillators of the right moving sector. The second index oscillators of the left moving sector. So they arise from somewhat different origins. So this is the beginning of this construction, and I will serve as our introduction, and I now will turn to the real construction and what happens. So are there any questions?
So in terms of motivation, I think Chris, how part of the motivation was sort of the landscape. Okay, I don't remember if he talked about it, but people are certainly considering the possibility that these new double theories might provide a larger class of string theory in vacuum. So do you have any comments on that?
Not really. You know, I think the idea I have in mind, and probably Chris's as well, I don't know if he said something about more general vacuum of closed string theory, is certainly we have problems thinking about deformations through backgrounds that include winding. That's much harder to do than normal deformations. So if you add a vertex operator that has momentum and winding, what are you deforming? You're certainly not deforming an ordinary metric, because the ordinary metric just depends on x. So there's certainly a very interesting problem of what could be backgrounds associated with winding modes that would be more naturally treated here. But having said that, my present interest is in just trying to understand this new kind of field theory that we have in hands, in which we consider both momenta and winding simultaneously, which is something that is supposed to be difficult to do in principle, because those things are not mutually local degrees of freedom.
But is it fair to say that this is only one example of this with the sine-Gordon model, where you've got topological solitons and excitations, and you study both at the same time? Then this would be an example of that.
Right. Yeah.
So from that point of view, I don't understand this condition. P comes. Let's say there's no simultaneous winding, but there's only one circle.
If there's one circle, there's no simultaneous winding and momentum. So that is familiar. Your states have now. The states of your theory either have momentum and winding, but you have all kinds of states. So you must construct a field theory that has momentum states and winding states. That changes as soon as you have 2 dimensions. Now every field can have momentum and winding. Nevertheless, even the case of one-dimensional theory is a little non-trivial, because in fact, all the field theories that have been written so far are for fields, all of whose excitations have either momenta or winding. But what we want is that a field theory for excitations in which you can have momenta or winding in every excitation. So your fields are a little more general here, even in one dimension. So let me do something that you would probably do if you were faced with constructing this theory, and probably will give you some intuition. And then we'll. So suppose you want to construct a theory. You have double field theory. You're going to have double gauge transformations. So you're looking for a theory, perhaps with double diffeomorphism. So let me remind you of the normal theory. If you have Einstein's theory and you do Gij, eta ij plus hij, then you have a quadratic Einstein theory, which is of the form four terms that are familiar. And one last term, 1/2 h di dj hi. Now I will write this as integral dx of something that we call r based on this derivative, the normal derivatives. Is the expansion of the curvature and the determinant of the metric to quadratic order using this kind of derivatives. Now, we are looking for a theory that has, certainly Einstein's theory has this much symmetry to this order. So, if we are going to have double fields and double diffeomorphisms, double gauge parameters, we're naturally led to believe that maybe this theory could support another set of diffeomorphisms based on the other derivatives. Now the question, and now all of these things will be functions, h, epsilon I, epsilon j are all functions of x and x tilde. Now, how do we go about thinking of this? Well, the obvious thing to attempt is to say, well, I'm going to write a theory now. The natural guess is a theory that is integrates over x and x tilde, and perhaps is r based on this derivative plus r based on the other derivative, the tilde derivative. Now, if you were to do these variations, for example, you try this variation on the action, well, this term, r, will be invariant. If you try this variation, the delta variation, since this is built with this tilde derivative, that will be invariant.
Directions in d and d tilde. So you should have additional interference term in your construction.
I did not omit it. I will find immediately that this is not enough.
Okay.
And we'll have to add terms like that. So I will do the following now. I will just look at what this variation does to the theory, for example. And of course, this first term is the one that fails. You'll have delta tilde of s would be equal to dx tilde of delta tilde of r of normal derivative. And what do you get? It's actually interesting to see what you get. And maybe I need a little more chalk, which is probably stored somewhere. Some color. Let's collect all the chalk. It's not too much, but
You want what?
Chuck, is there a box in there?
yeah, I think, yeah, here, it's more chalk. All right, so what do we get here? Well, it's interesting. You get the following. D tilde j hij dk di epsilon k tilde minus dk epsilon I tilde plus di dj hij minus d squared h del dot e tilde plus di hij minus dj h d dot d tilde of e tilde j. Okay, have a look at this for a moment. Actually, the fact is that when you do this variation, when you do, of course, the delta of r, every term cancels. Beautifully. When you do this delta on this, no term cancels. Everything goes wrong. So how wrong? Well, that's wrong. And then you basically discover what is the fix for this. The fix for this, it just cannot be fixed at this stage unless you add new fields. And what you're going to add is a field Bij, whose gauge transformation under tilde is going to be di epsilon k tilde minus dk epsilon I tilde. And you're going to try to cancel this term by adding a term in the action, which will be of the form d tilde j h ij dk of this b I k. If you put a minus here, it will all work. So a new term with a B field can be used to cancel this. This can be canceled if you introduce another field, a dilaton, whose gauge transformation is essentially this. And this term, you can try to cancel, and we've tried, but you can't, actually. Once you add things, it just keeps giving you bad problems. But now we know that this term cannot be canceled, or at least if you manage to cancel it one day, you will have discovered something extremely important because of this condition. Everything has to be killed by those things. So even this naive attempt to construct the double field theory of gravity has taught you something. First, if you have double diffeomorphisms, you cannot realize them, as far as we can tell. This is not a proof, but it's a very strong argument, just with a metric. You need the antisymmetric tensor field, and you need the dilaton. So double diffeomorphism is the symmetry that requires the massless multiplet of string theory. Moreover, there's no escaping this constraint, as far as we know, and we see the role of it. So this, now I did not complete the construction here because the string theory, the string field theory, actually tells you how to do this a lot more efficiently. So I'm going to give you just the answer now, well, nicely written so that you can see what this is. So this should be thought as a motivation for the result that I will now write very explicitly. And here is the free theory, written very explicitly. This is section 3 as dx tilde r of d as we had plus r of d tilde as I mentioned. Then there's the Kalb-Ramond field strength, bij d squared bij plus 1/2 dj bij squared. That's the h squared of Kalb-Ramond, plus terms with d exchange for the tilde here, just like you did here. And then come mixed terms that are exotic and don't exist in the conventional theory. The tilde b plus d. These terms have one normal derivative and one exotic winding derivative. Those were a question before. Di dj tilde bij. So in the normal free field theory of the massless sector of a string theory, you basically have I'm probably let me see one thing. Yeah, my notation is a little funny. I really mean there's a little bit of dilaton in these terms that you probably better look at the paper to get it all straight. But because I didn't write the dilaton square term, so you sort of can incorporate them into the definition here. So here is the theory with funny couplings that only exist if you have both momenta and winding. A mixture like this to the dilaton and a mixture between H and B that doesn't exist in the conventional theory. So what are the symmetries of this theory? Let me write the conventional ones that you would have. Delta Hij, delta Bij, and delta D. We know in the normal theory that there is a symmetry, the Kalb-Ramond symmetry, which would be di epsilon j minus dj epsilon I. That's a symmetry under Kalb-Ramond gauge transformations. Under this symmetry, the dilaton doesn't do anything, and the graviton doesn't do anything. Moreover, there's another symmetry, sets of symmetries, ones in which the metric transforms under diffeomorphisms to linearized order, in which the Kalb-Ramond field is not supposed to do anything, and the dilaton, well, yes, it does a little bit. These are the conventional gauge transformations of a theory. This is the parameter of Kalb-Ramond gauge transformations, and doesn't affect the metric, doesn't affect the dilaton. And these are diffeomorphisms that to this order affect the dilaton but don't affect anybody else. So what changes now in this field theory? This would not be a symmetry. So here is what changes. These symmetries over here, you would have, I want to use a different color, maybe a yellow, B tilde I epsilon tilde j plus D tilde j epsilon I tilde. So there they are, the double diffeomorphisms. The diffeomorphisms with these parameters, and these parameters are the ones that would be the Kalb-Ramond gauge parameters under conventional transformations, but now that they're tilde derivatives, they appear exotic here. And in fact, they appear exotic here as well. Moreover, here, diffeomorphisms in general don't affect a tensor like Bij to this order. There's no inhomogeneous term. But if you have the double theory, yes, they do. And they affect them through the tilde derivative. So d tilde Ej minus dj tilde Ei.
1/2 positively epsilon tilde without a minus 1?
This is minus 1/2, and this is plus 1/2. Very important. It's conceptually, dramatically important, that sign, as I will show now. Why? This is sort of the familiar ones you know with normal derivatives. And in this case, we define the dilaton, the scalar dilaton, which is d plus 1/4 of h, the trace of this. And this is gauge invariant. So delta, I'll put here delta tilde. Delta of phi is 0. This is the so-called scalar dilaton. Nevertheless, in here, because of this sign, there is a phi tilde that would be equal to d minus 1/4 of h. That would be delta tilde of phi tilde is 0. But the signs are different. So what it results at the end, that in double field theory, there's no scalar dilaton, that is scalar under both diffeomorphisms and dual diffeomorphisms. And that's a very significant difference with respect to the conventional theory. In the conventional theory, you do have a scalar dilaton. Here, the best you will have is that the dilaton will be a density, but it will not be a scalar. So I want to write the theory once more, this free theory, with very general notation, so that you can see now the spirit of this whole construction. Maybe I should not exploit that word and just continue here. So if you want very efficient notation for general backgrounds, well, you will use the following. Some derivatives that really have background dependence. These are the derivatives that arise naturally in closed string theory. These are the background metrics and antisymmetric tensor fields. So this derivative just ignores this, and I just put it in this place so that you can see the index contraction, how it goes. These are naturally defined with the index down, and you can use this metric Gij, which is the inverse of Gij, to raise and lower indices. So you can define di equals Gij dj, and d bar I equal Gij d bar j. If you do this, you also have things like d squared would be di di, and d bar squared equals di di, like that. So what does it do this for you? Well, it simplifies things quite nicely. The operator delta that we're so concerned about, which is minus 2 di di like that, can be written in terms of these operators very neatly. And it's nothing else but 1/2 of d squared minus d bar squared. If you define the box as 1/2 d squared plus d bar squared, if this constraint holds, that delta is equal to 0, remember we want that, if that constraint holds, this is equal to d squared and is equal to d bar squared, in fact. So this is very general. And then the free action formulated for a general arbitrary background. You see here, I wrote this in sort of a flat g mu nu was equal to eta mu nu plus h mu nu, and there was no background antisymmetric tensor field. But here, we're going to write the whole action. It's going to be simpler to write and very neat. So here is the whole action. S2 is equal dx, dx tilde, 1/4 Eij box Eij. Remember, this is the field. This has its indices raised. Plus 1/4 d bar j Eij squared plus 1/4 di Eij squared minus 2 little d di d bar j Eij minus 4 d box d. That is the whole action. You know, it was a lot longer here, especially if you think that each one of these has 4 terms. 4 terms is 8. 2 terms is 10, 12, 14, 15 terms. They've collapsed into this. It's the elegance of the string formulation that does that. What are the gauge symmetries now? You have delta lambda equal d bar j lambda I, delta lambda of the dilaton minus 1/4 d dot lambda. Delta lambda of Eij. Delta lambda bar of Eij. So there are symmetries lambda and lambda bar. These are the symmetries we've seen before, but collected in a more efficient way. By the time you collect it this way, actually the signs look the same. That doesn't mean still there is a dilaton, because actually what's happening is that with the EIJ, there's no way to trace these indices. They are of different type, the two indices, the I and the J. They behave differently. So there's still no dilaton, but the symmetries are like that. And this action now represents fluctuations around an arbitrary background. That background shows up in the derivatives. So this is a very general action, a lot more general than this, and its symmetry is fairly easy to check. So now let me say a few words about the interactions and what they do. So this is the free theory. We've learned a nice amount of statements and facts about this theory, but you could say, well, there is this symmetry, and every field satisfies delta of EIJ is equal to 0, delta of the dilaton is 0, this constraint. Well, you might run into trouble at the cubic level. The theory will not exist if you try to build an interaction. Happily, that's not the case, and we succeeded in constructing the full cubic theory, and it still works quite beautifully. And I want to basically say that, and that's pretty interesting. So let me show you what happens then. So what is the cubic action? Well, the thing to note about the cubic action is that if you were writing the cubic action of Einstein plus antisymmetric tensor plus dilaton, it would take 3 blackboards. But here it's very efficient, and it takes a couple of lines, basically. I will not write it completely still, because it would take me 2 minutes instead of 1. I'll write the complete cubic action for the gravity and antisymmetric tensor. Is this one term, dIEKL, d bar L EKJ, and minus d bar K EIL, d bar J EKL. That's it. 3 terms. If you just write the cubic action for gravity alone, I think it's the most efficient way is like 12 terms. If you insert the cubic couplings of, here it's all the terms with 3 gravitons, with 2 gravitons and 1 Calbramon, with 2 Calbramon, 3 Calbramon, and everything is in here. Then there's a term plus 1/2 d, d times quadratic in E, couple of terms more, and then 1 term with 2 d's, and 1 term with 3 d's. And that's it. So the action is quite tractable. How about the gauge transformations? Well, the gauge transformations are a little surprising, because they're not the standard ones that you would expect. And this is a feature of the theory that is probably quite good. So what do you get for gauge transformations? Let me write the analog of these gauge transformations with lambda I parameter. So here it goes. Delta lambda EIJ is equal to dj lambda I plus 1/2 di lambda k EKJ minus dk lambda I ekj plus lambda k dk eij. Let me write the other one, delta lambda of the dilaton minus a quarter d dot lambda plus 1/2 lambda dot d d. Now, there are, so that's it. To this order of the calculation, those are the gauge transformations. There's also the other gauge transformations that you can write if you know these ones, because this symmetry, because of the orientation invariance of closed strings that said you can replace holomorphic by anti-holomorphic, you can essentially change bars to unbars and recover one symmetry from the other. So as long as your action preserves this orientation invariance symmetry, which this one does, you can find the other gauge transformations just by transcription. Now, these terms don't quite look like the ordinary Lie derivatives of a metric. In fact, if you remember these things, this looks like a transport term of a Lie derivative. This is a transport term. But these ones are a little off. This one looks pretty reasonable, actually. The derivative should pull one of the indices here, and the parameter is added. But here is totally wrong. So this is sort of a wrong term as far as Lie derivatives is concerned. And this is the transport term. So actually, you don't quite seem to get diffeomorphisms, but there's nothing to worry. Actually, diffeomorphisms are there. And the fact is the following. Basically, this theory, although I have not explained why, is totally T-duality invariant. I will say a few words about it, but if you believe me for a second that it's T-duality invariant, what I'm going to show here, what one can show rather easily, is that if you restrict yourself to a conventional frame, you recover diffeomorphisms. So what is that statement? The statement is the following. For example, if you now have this and the delta bar symmetries, and you assume that all fields don't depend on x tilde, then take lambda equal lambda bar equal epsilon. Then what you find from these transformations is that delta epsilon of eij plus 1/2 eik ekj, you have to do a little variation, is in fact di epsilon j plus dj epsilon I plus di epsilon k, I'll call this e kj plus, I'll call this eij plus, so you get ekj plus dj epsilon k epsilon ik plus ek dk epsilon ij plus. So actually, by the time you choose delta tilde equals 0 on these parameters, there is a field redefinition that constructs the conventional graviton fluctuation that transforms with precisely the Lie derivative. Yes?
You just mean convince on the x and x tilde have been exchanged? Or?
Yes, it's even more than that, of course. It's the full SODD. So exchange of x and x tilde is the simplest T-duality. And so here, that's one thing that happens. And for example, if you do the other case, if you consider d equals 0 now, so that there are only d tildes, and you take lambda equal minus lambda bar equal epsilon tilde, then you find that delta epsilon tilde of eij minus 1/2 ekj has the correct Lie derivative. So actually, this formula that I wrote on the top of the blackboard is smart enough to reduce in every possible T-dual frame to conventional diffeomorphisms that you must have when the theory just depends on either x's or x tildes. But in the big theory, before you make any choice, the formula is different. Now, I want to conclude by making a couple of remarks, perhaps around here. T-duality is a manifest symmetry of the theory in the following sense. If you have an ODD transformation, it's matrices of size d times d that form a 2D plus times 2D matrix. The transformations of backgrounds go like this. It's a matrix transformation, CE plus d to the minus 1, and x tilde x prime is equal to G matrix x tilde x. So if you have this action that I wrote an action that depends on the background through the covariant derivatives and the fields Eij and D. There is a very important matrix here, a couple of matrices in fact, called M and M bar, which are of the form dt minus ECT and dt plus ETCT. And in fact, the derivatives transform with this matrix. The T-duality transformations of these fields are generated by these matrices. And the metric, which is used to contract English, is transformed with these matrices under T-duality. So at the end of the day, this is just equal to the action of E prime with the transformed dual fields. And it's a matter of just index contraction. So the claim is the following: T-duality is just a consequence of the index structure matching in this form. Nothing else. One last remark. That is the thing that makes life really interesting and difficult for next order. I claim, I've not explained every detail, that this construction to cubic order is totally safe and has no problems whatsoever. You've constructed an interaction of fields that have x and x tilde, and you've preserved this double diffeomorphism symmetry to first nonlinear order. The question is whether you can go further. Now, most people, including myself a few months ago, would have said, if you can construct the first non-trivial interaction, you're surely not going to have problems later. I would like to revise that. Even though we don't have necessarily a problem, things get a lot more non-trivial at the next order. And the reason is the following. There's a little sleight of notation in the formula that I wrote, which is the following. You remember the constraint that every field must be annihilated by this delta operator, which is second order. So this was okay because lambda is annihilated by the delta operator. Delta commutes with derivatives, so everything is consistent. But here it's not obvious, because if lambda is annihilated by delta and E is annihilated by delta, the product may not be annihilated by delta, because this is a second-order differential operator. So in general, you must put a projection. You must calculate this, and you must project to the subspace of the kernel of delta. So this parenthesis that I put here, if I want to be really precise about what I'm talking, I should call it a projection to the subspace delta equals 0, and I should put it here as well. Now, this doesn't affect the cubic action, mind you. There's no need to complicate this. This action is perfect, actually, because you have a product of this satisfies the constraint, this satisfies the constraint. The product may not. But since they are integrated against something that satisfies the constraint, that picks only the right part. So there's no need to change anything here. The cubic action is OK. It is the quartic action that is going to know about these projections. And therefore, it's not a trivial theory that you will just write it out and it will work out. Nevertheless, it is fairly, I think, non-trivial that the construction has worked to this order. And I would expect that it works to all orders. And in doing so, we will understand what happens at the full nonlinear level with this symmetry. Even at this order, this thing has a funny gauge algebra. The gauge algebra is not the usual Lie bracket gauge algebra, but it's different. And it's already teaching us a nice set of, it relates to a nice set of ideas, in particular to, in the mathematics literature, to Courant brackets, Courant bialgebroids, and funny things that might be needed to do this. At the end of the day, we will, if this succeeds, we will have a theory that is perhaps a little non-local, because it will involve momenta and winding simultaneously. And this non-locality may appear a little through these projections that restrict you to the kernel. So that's all. Thank you very much.
Basically, you said that there is no region this effective field really capture, only derived degrees of freedom.
Well, it's not, there's no region in momentum space in which this is all light fields. So if you think of this as a truncation of string theory, say, in string theory you have higher mass levels, and you're looking at a massless sector. Nevertheless, by including momentum and winding, some of your excitations might be as big as one of a massive level of a string that you have not considered.
So you actually mean a consistent application of some subsector, which is
not necessarily a low energy sector. So basically, if you have an effect, let me say it this way. I don't know, the issue here might be an issue of symmetry, but if you have a theory, basically the only thing that is difficult to integrate out is a massless field. All massive fields can be integrated out. But it could conceivably be the case that if you have a theory with some massless excitations and an infinite number of massive, you may decide to keep the massless and a few massive and integrate everything else. So in a sense, that would be sort of the spirit of what we're doing. If it has to do. Now, if this theory really exists to all orders with momenta and winding, it's probably because of some symmetry reason. And that symmetry reason remains to be discovered. Yes?
Have you tried to thought about it in the context of ADS free 52? But also in the bulk string theory, there was analogous to winding state of string theory. Theoretically, really become also the proximity of the boundary theory. And you can argue for consistent application of some subsector of boundary to the natural theory. Well, yeah.
don't have anything to that. Yeah.
Just a quick technical question. You've introduced this dual variable psi, is it psi or x tilde, but there's no tangent space in these things, right?
Well,
For the IJK, they're still under the original range of the
oh, that's right. So, absolutely correct. So we've sort of, in the original theory, you have Eij of x, and now you have Eij of x and x tilde, and the indices have not changed whatsoever.
Wouldn't it be natural to let them?
That's true. So, in fact, most naturally, so this is all that really is there in the theory. But the thing that people have tried to argue in the past is that if you double, perhaps you should consider a bigger metric, Hij, that is maybe has the Eij here, and Ei, some new kind of index, and a double thing. And in fact, there's a natural metric over here that is familiar in T-duality, is the so-called generalized metric, which is G minus 1 BG, and GB minus 1, and G minus 1 here. So there's some natural metric like that. There's been nice work of Siegel and others in which this metric has been extended to a doubled structure in order to put more gauge invariances and more symmetries in order to reduce to this theory on. So while we really don't have them, at least formally, it probably is a very good idea to put those fields in and maybe new gauge symmetries and gauge them away or do something with them, because at the end of the day, they're not there. And the reason we didn't do yet this is because in the string theory, naturally, say in the vertex operators, in the string field theory, those extra fields don't appear. So at this moment, we pretty much would try to do things with a minimal amount of stuff. But it's quite possible that if you want to find the full nonlinear structure of this or other things, that you should be using more. It's, in fact, that's sort of the way, there's two people that have done work that is relevant to this, is Zeitlin and Siegel. Zeitlin was the first one, in a sense, that argued strongly that you should consider these kinds of fields and didn't get too far. Siegel gets very far, but he really assumes that at the end of the day, you really have x's or x tildes. And then the theory simplifies enough that he claims a full construction. But the theory that he does has still some nice T-duality symmetries. But it's not the complete theory we're trying to get here. But in fact, Siegel uses some sort of generalized structure in which the indices get doubled. And it's probably a very good idea.
Another quick one. This sounds a bit reminiscent of what Stringer and Swansinger did when they tried to construct a quantum field theory of magnetic and electric charges with dual gauge potentials for the magnetic ones, and then some more propagating gauge condition to get rid of extra degrees of freedoms. But ultimately, I think that wasn't successful, if I remember correctly.
Was or was not?
I think not. I can't remember.
Yeah, it probably is very difficult. And I don't know what will happen here. So it's you're really trying to do something very non-trivial. So, for example, there's another issue. For example, so let me say it this way. Certainly, the full string theory manages to do that. So I would say that by definition, the full closed string field theory is the double field theory of all component fields, and that exists and is gauge invariance and succeeds. The only question we have is whether we can find something a little simpler than the full closed string theory that has this much in it. So let me mention one more trick that the string field theory uses to get this to work, and it's the issue of co-cycles. When you have mutually non-local vertex operators like momenta and winding, the string theory to higher orders, cubic and higher interactions, uses co-cycle factors to fix sort of the non-locality of that. And it is known that those co-cycle factors play a role in getting the quartic structure of the theory to work. So one possibility, for example, of yet another ingredient that has not been mentioned here is that these co-cycle factors of string theory are necessary, because typically if you get a vertex operator and another one with momenta here, and this with winding, instead of sort of being like Grassmann even objects, they behave as Grassmann odd objects. This is explained in Polchinski. So you have to fix that. And it's part of the problems of dealing with both mutually non-local operators. So all these problems get solved in the full closed string theory, which is a double field theory. Our question is whether we can have a massless version of this that still makes sense. And if it doesn't, at least learn what is very non-trivial. Certainly, you could have thought that it would fall apart even by the time you try to construct an interaction, and it doesn't. So we'll have to see what happens next. Who knows? Yes?
Often if you put aside T-duality, you consider much simpler all before, like just as we did all before, we do the same thing, try to write a twisted set of just one small.
So you're saying, suppose you try to do a field theory which includes both twisted and untwisted sector of, say, a Z2R. Well, I wouldn't know to begin with what to think of the dual coordinate. What would play the role of dual coordinate?
2 points. Like you don't have all the integers.
2 points. Oh. 2 fixed points, or
maybe like a spin up and down.
maybe we'll leave it for a discussion later between us.
Any more really quick questions? Okay, so let's battle again.